In this lesson, we will discuss properties of certain arithmetic functions. Recall that we defined arithmetic functions as functions whose domain is a set of positive integers, or the natural numbers. So an arithmetic function is a function whose domain is a set of natural numbers Another name for these functions is a number theoretic function, but I'll stick to the term arithmetic functions. We've seen some certain arithmetic functions already. One of the most famous ones is the Euler-Phi function. There are two more arithmetic functions that arise naturally in certain investigations of number theory. The two functions that we're going to study in this lesson more extensively are tau of n, which is equal to the number of positive divisors of n, and the other arithmetic function is sigma of n, which is the sum of these divisors. We know that phi of n is the number of relatively prime integers between 1 and n to n, and tau of n will be the number of positive divisors of n, and sigma of n would represent the sum of these divisors of n. We also defined the term multiplicative for certain arithmetic functions. We call that an arithmetic function is multiplicative. So recall, an arithmetic function is multiplicative if f of m times n equals f of m times f of n whenever m and n are relatively prime. We've already shown that the Euler-Phi function, phi of n, is multiplicative. We'll actually show in this lesson that tau of n and sigma of n are also multiplicative arithmetic functions. Let's recap some basic facts about the Euler-Phi function. So we know that phi of n equals the number of positive integers less than or equal to n that are relatively prime to n. Okay, with this definition, we've proved certain facts. We know that if p is prime, then the numbers 1 through p minus 1 are all relatively prime to p. Therefore, phi of p will equal p minus 1. And we've shown that for a prime power, phi of p to the power n, for example, would equal p to the n minus p to the n minus 1. And if you factor out p to the n, another way to rewrite this is p to the n times 1 minus 1 over p. Since we have shown that phi is multiplicative, you can completely determine the values of the phi function if you have the prime factorization of an integer n. So phi of any integer n will equal n times the product of factors 1 minus 1 over p, where the product is taken over all primes p dividing n. So for any p dividing n, multiply by 1 minus 1 over p. And as I mentioned earlier, phi is multiplicative. So phi of m times n will equal phi of m times phi of n when m and n are relatively prime. So this is just a recap of some of the basic properties and formulas for the Euler phi function. We'll develop some of the similar properties for the functions tau and sigma. So recall, tau of n would be the number of positive divisors of n, and sigma of n would be the sum of the positive divisors of n. So let's look at some quick examples. So for example, tau of 1. Well, 1 is the only positive divisor of 1, so there's only one positive divisor of 1. Sigma of 1 would be 1 as well. Tau of 2, there's two divisors of 2, the numbers 1 and 2. So tau of 2 would equal 2. And sigma of 2 would equal 1 plus 2, which is 3. Tau of 3, well, any prime number only has two positive divisors, 1 and itself, so tau of 3 would be 2 as well. Sigma of 3 would therefore be 1 plus 3, which is 4. Tau of 4 is 3, because the numbers 1, 2, and 4 divide 4. Sigma of 4 would equal 1 plus 2 plus 4, which is 7. Tau of 5, again, for any prime, we see that tau of a prime would just be 2, and sigma of 5 would be 1 plus 5, which is 6. One more example, tau of 6 would equal 4, and sigma of 6 would equal 1 plus 2 plus 3 plus 6, which is 12. So as I mentioned, if p is prime, then p would only have two positive divisors, so tau of p would always equal 2, and sigma of p, the only divisors would be 1 and p, so it would equal p plus 1. We can do even better than this. So more generally, the positive divisors of a prime power of, say, p to the n are 1, p squared, all the way up to p to the n. Hence the number of positive divisors, so the tau of p to the n is n plus 1. And if we add up these positive divisors, so sigma of p to the n, we would get 1 plus p squared up to p to the n. But I can rewrite this as the quantity 1 plus p squared all the way up to p to the n times p minus 1 and divide by p minus 1, and we get the formula for the finite geometric sum. If you multiply out the numerator, you'll get p to the n plus 1, and all the other terms except for minus 1 will cancel. And so we see that sigma of p to the n can be written as p to the n plus 1 minus 1 all over p minus 1. So now we have formulas for tau of a prime power and sigma of a prime power. Once we can show that tau and sigma are multiplicative, that will enable us to completely determine the values of these functions. So first, we need to prove the following theorem. If f is multiplicative, and capital F is defined by the following sum, capital F of n is defined as the sum over divisors of n, and you're adding up f of d, then capital F is also multiplicative. So let's begin with a couple of relatively prime integers. Let GCD of m and n be 1. Then we need to show that capital F of m times n equals capital F of m times capital F of n. So let's begin with capital F of m times n. And by definition, this equals the sum of f of d, where d is a divisor of m times n. But recall, m and n are relatively prime, so if d is a divisor of m times n, then I can write d as a product of factors d1, which is a factor of m, and d2, which is a factor of n, and they must be relatively prime. So since m and n are relatively prime, every divisor of mn every divisor d of m times n can be written uniquely as the product of a divisor it's called d1 of m and a divisor d2 of n, where d1 and d2 are relatively prime. So the GCD of d1 and d2 is 1. Moreover, the product of any two divisors of m and of n is also a divisor of m times n. The product of two divisors of m and of n is a divisor of m times n. So then I can rewrite the sum above. So capital F of mn is the sum of divisors of m times n of f of d. Then I can break up each d as some product. So I can write this as f of d1 times d2, where d1 is the divisor of m, and d2 is the divisor of n. Since d1 and d2 are relatively prime and f, little f, is multiplicative, I can write this sum as the sum of d1 dividing m and d2 dividing n of f of d1 times f of d2. This in turn can be rewritten as the sum of f of d1, where d1 is a divisor of m, times the sum of f of d2, where d2 is a divisor of n, and this, by definition, is capital F of m times capital F of n. Therefore, capital F is multiplicative. So I'm going to use this theorem to prove that tau and sigma are both multiplicative. So corollary, tau of n and sigma of n are multiplicative. So I'm going to write tau of n as the sum of 1, where the sum ranges over divisors of n. So this will count the number of divisors of n. And I'm going to rewrite sigma as the sum of d, where d ranges over the divisors of n. Since the functions inside the sums, I'm going to call them f1 and f2, defined by f1 of n equals 1, and f2 of n equals n for all natural numbers n, since these two functions are multiplicative, then by the previous theorem, tau of n and sigma of n must be multiplicative as well. So we know that tau of n and sigma of n are multiplicative. Now we will prove the general formula for any natural number n of these two functions. So if I have the prime power decomposition for n, so n equals p1 to the a1 up to pr to the ar power, then tau of n will equal a1 plus 1 times a2 plus 1 all the way up to ar plus 1. So in product notation, I can write this as the product where I goes from 1 to r of ai plus 1. And the general formula for sigma of n looks like sigma of n equals p1 to the a1 plus 1 minus 1 over p1 minus 1 times all the way up to pr to the ar plus 1 minus 1 over pr minus 1. Again, using product notation, is the product where I goes from 1 to r of the factors pi times ai plus 1 minus 1 over p minus 1. So these formulas will follow from the formulas for a single prime power and the fact that tau and sigma are multiplicative. So these formulas follow from the fact that tau of n and sigma of n are multiplicative, and the formulas tau of p to a power equals n plus 1 and sigma of a prime power equals p to the n plus 1 minus 1 over p minus 1. So if we take tau of n, then we can break up tau over each one of the prime power factors, and likewise we can take sigma of n and break it up as sigma of p1 to the a1 up to sigma of pr to the ar. And this establishes the general formula for tau of n and sigma of n. So let's see some examples. Let's look at tau of 60. So the number of positive divisors of 60. Well, 60 is 2 squared times 3 to the first power times 5 to the first power. So by the formula for tau, we see that this must equal 2 plus 1 times 1 plus 1 times 1 plus 1, and 3 times 2 times 2 is 12. So 60 has 12 positive divisors. Sigma of 60, if I add up these divisors, again we see that this is sigma of 2 squared times 3 to the first power times 5 to the first power, and I can write this as 1 plus 2 plus 2 squared times 1 plus 3 times 1 plus 5. So this equals 7 times 4 times 6, which equals 168. So tau of 60 is 12 and sigma of 60 is 168. Let's use a bigger natural number. Let's try tau of 5040. Well, the prime power decomposition of 5040 is 2 to the 4th times 3 squared times 5 times 7. So this will equal 4 plus 1 times 2 plus 1 times 1 plus 1 times 1 plus 1, which is 5 times 3 times 2 times 2, or 60. So 5040 has 60 positive divisors. What do I get when I add up those 60 positive divisors? Sigma of 5040, again, is sigma of 2 to the 4th times 3 squared times 5 times 7. So this will equal 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the 4th times 1 plus 3 plus 3 squared times 1 plus 5 times 1 plus 7. So I can use the finite geometric formula, 2 to the 5th minus 1 over 2 minus 1 times 3 cubed minus 1 over 3 minus 1, and times 6 times 8. So this will equal 31 times 13 times 6 times 8, which gives 19,344. Next, we will prove a formula involving the Euler-Phi function that we used when we were proving that every prime number has a primitive root. Here's the theorem. The theorem says that if you add up phi of d, where d is a divisor of n, then you will get n. Let me give you a quick example. For n equals 6, the sum of phi of d, where d divides 6, well, that would be phi of 1 plus phi of 2 plus phi of 3 plus phi of 6, and phi of 1 is 1, phi of 2 is 1, phi of 3 is 2, and phi of 6 is 2, and we see that this does indeed equal 6. So there's a quick example of this theorem. Now we're going to give the proof. So in this proof, we're going to partition the numbers 1 to n into different classes. So we will split up the integers 1 to n into classes. So for each d that divides n, for each divisor d that divides n, we're going to define a set where we define S of d to be the set of integers between 1 and n whose greatest common divisor with n is d. So in other words, S of d will be the set of integers m such that m is greater than or equal to 1 and less than or equal to n, and the greatest common divisor of m and n is d. So for example, with n equals 6, we would have 4 of these subsets. So S1 would be the integers relatively prime to 6, so there'd be 1 and 5. S2 would be the integers 2 and 4. The greatest common divisor of 6 and these integers is 2. S of 3 would be the set containing 3. And S of 6 would equal the set containing the number 6. So you can see from this example that each of the integers 1 to n will show up in exactly one of these sets SD. And so these sets SD completely partition the integers 1 to n. So then the various sets SD partition the integers 1 to n That is, every integer from 1 to n is in exactly one of the SD. Okay. So every integer from 1 to n is in exactly one of these sets SD. So let's talk about the size of these sets SD. So the notation for the order or the size of SD is a set SD with like absolute value bars. So if this denotes the order of SD, which is the number of elements in SD, then it's clear that n will equal the sum of the orders of these SD, where D runs over all divisors of n. Okay, so this works again because the SD partition the numbers 1 to n. So if you add up all the number of elements in each one of these SD, you'll get a total of n. So if M is in SD, then the GCD of M and N is D. So the GCD of M and N equals D if and only if the greatest common divisor of M divided by D and N divided by D is 1. Okay, so we proved this earlier in this class. The GCD of M and N is D, then the GCD of M over D and N over D is 1. In other words, M over D is relatively prime to N over D. Thus, M will be in the set SD if and only if M over D is relatively prime to N over D. So if I want to count the number of elements in SD, I can just count the number of elements that are relatively prime to N over D. But we have a notation for that. Thus, there are phi of N over D, so that's the number of elements that are relatively prime to N over D. There must be this many elements in SD. So let's replace the order of SD with this quantity. Then n, which we said equals the sum over the divisors of n of the order of SD, equals the sum over the divisors of n of phi of N over D. What remains to show is that this sum will be the same as if I replace phi of N over D with just phi of D. As D assumes values of various divisors of n, so does the complementary divisor N over D. So the sum of phi of D, where D varies over the divisors of n, will thus be equal to the sum of phi of N over D, where D ranges over the divisors of n. And then from these last two equations, we get the result.